In last section, we discussed about single stage OPAMP or normal differential amplifier itself, and we found different type of OPAMPs, cascaded OPAMP, folded cascaded OPAMP, OPAMP with a single-ended output with the help of current source load, etc. we discussed. In this section, we are going to discuss two-stage OPAMP. The two-stage OPAMP, it consists of two differential amplifier stages, and the design constraint or design concept of two-stage OPAMP is that the first stage will provide a higher gain and the second stage is nothing but a common source amplifier. Okay, it will be a common source amplifier such a way that it will give high output swing. High output swing. Okay, high output swing. Okay, that's all. So common source amplifier, the basic common source amplifier look like this one, and here it will be in this one. This will act as load. This current source configuration will act as load, and this PMOS act as the input. This PMOS act as input, and I drawn common source amplifier like this one instead of NMOS. I drawn it with the help of PMOS because this configuration we are going to use in differential amplifier case. So if we consider a two-stage OPAMP, this is the two-stage OPAMP circuit diagram. In two-stage OPAMP, if we consider the middle portion, it's simply a normal single-ended differential amplifier, not single-ended, is a differential two-ended differential amplifier. Okay, and here the load is a current source load. Here you can write a diode connected configuration or you can use cascaded configuration. Anything is fine. For simple circuit, we are considering a current source load. And second stage, it will be a common source configuration, right? Common source configuration with a PMOS as the input. Okay, PMOS common source configuration, that output Vx and Vy are connected to that common source configuration. And if A1 is the gain of this one and A2 is the gain of common source configuration, then the total gain A equal to A1 into A2. In case of this circuit, the gain of this configuration we know it is GMN because input is given at n side. GMN1 I given. Okay, GM1 into R0 N1 parallel to R0 P1 because this output impedance is R0 P1. P1 indicate in the first stage. Okay, and this is a common source configuration. In common source configuration, we can find the equivalent gain or the amplifier gain, and here also it is equivalent to here the input is given at this PMOS and this will act as a load, and its load impedance is something like R0 right, it's a current source configuration R0 P, not P, it is N, R0 N of 2. So here also we can write it is gain is something similar to this one. Here it is G M of P in second, which is R0 P2 parallel to R0 N. Okay, then if we multiply these two, we will get the overall gain. So this is the gain calculation. The first stage we calculated AV. I'm using half circuit analysis. We will get the first stage gain is minus GMN1 R0N1 parallel to R0 P1. And similarly, in the case of second stage, we can find the output of one of the common source stage, that is minus GMP2 into R0 P2 parallel to R0 N2. When we multiply this one, we will get the overall gain. And we introduced this two-stage OPAMP not for improving the gain. The main aim of two-stage OPAMP is to improve its output swing. Here the output swing, here we will measure what is the output swing of this circuit. Okay, here we will measure what is the output swing of this circuit. The output swing or the output stage This is the output stage. Output stage consists only two MOSFET. Okay, one stage in upper half and one stage in the lower half. So the output is limited only by the overhead voltage of this transistor and this transistor. So the maximum output swing is VDD minus the upper and lower overhead voltage. So it is 2 V overhead voltage, and twice of this one will be the differential voltage output. Okay, two-ended output. So there is a drastic improvement. In the cascaded case, we found that every transistor is added, the output voltage starts decreasing. But here, due to the common source configuration, the output swing increases drastically. Okay, so the total output swing is 2 times VDD minus 2 overhead voltage. And only one more circuit we need to discuss is that it's two-stage op-amp with a single-ended output. Okay, two-stage op-amp with a single-ended output. In this configuration, we are making the single-ended output in the second stage. Here we are making the single-ended output. Okay, single-ended output. Here usually a normal MOSFET whose gain is same as that of the previous case, GMN 1 R0 N1 parallel to R0 P1. And the second stage is designed using with the help of a current mirror. Here if you look here, it is a current mirror, right? With the help of a current mirror, and input is from here. Okay, input is from, my mistake, input is from the PMOS. Input is at a PMOS. So here also we will get the effective transconductance will be same, or the gain will be same. Effective transconductance will be equal to GMP, and output impedance is same as that of, here the output impedance is same as that of, if we evaluate the output impedance of this one, here the output impedance at this direction is 0 N1 N2, and this direction it is 0 P2. So the total output R out, effective output impedance of this one is R0 N2 parallel to R0 P2. Okay, and next to find the gain of the second stage, we need to find the effective transconductance. To finding the effective transconductance, we are just redrawing that circuit. Here Vx input is given. Due to that Vx input from here, the current is, here it is plus GM5 Vx. Here it is GM5 Vx, and here the current is GM6 Vy. This configuration here I clear all. Due to this circuit, current at this point is GM5 or GMP P5 Vx, and this current is GMP6 Vy, and we need to find the short circuit current to effective, evaluating the effective transconductance with respect to Vx and Vy. Okay, Vx and Vy, and this current I need to evaluate I out. GMP6 Vy is here. Due to the current mirror configuration of these two, M7 and M8, this current is GMP5 Vx. So from that we can evaluate I out. I out is nothing but it is GMP5, or I out here it is GMP6 Vy is sum of these two, and we can rewrite I out is GM5 Vx minus GM6 Vy, or we can write it as I think there is a mistake in here also. I out plus GMP6 is equal to GMP5 Vx. So this is fine, and I out is GM5 Vx minus GM6 Vy, and we will get I out is GMP, or it's common. Okay, GM5 and GM6 we written as GMP Vx minus Vy, or the effective transconductance is GMP itself. Note here it is positive because we are using common source configuration. Okay, and due to that the gain of the OPAMP, gain of the single ended configuration is also same as that of the differential output, and the output resistance is R1 parallel to R12 parallel to ROP2, because only output side we have only these two configuration. Okay, these two elements are there, and limitation is there is a here also in this configuration also we have shorting issue, shorting between input and output. It will create reduce the output swing, reduce output swing, and so buffer configuration is not possible. The remedy circuit is not available in our textbook. Okay, and we don't want to discuss that also. And the last topic in this module is gain boosting. Gain boosting without adding, without adding extra cascaded configuration. Okay, in gain boosting method we can increase the gain of the amplifier without adding more cascaded device, and here we are using, and additionally we are using an auxiliary amplifier to improve the gain. The idea is that if we add an auxiliary amplifier between the cascaded stage, so instead of cascading 10 stages, just we are adding an amplifier here, then this differential amplifier have a property. It will, due to the virtual short concept, it will maintain the value of, due to the virtual short between the terminals, it will maintain a short circuit between these 2 points, or under any condition it will maintain the value of IA Vx voltage. So there is no change in current. Vx is same and our current is, so the resistance is also remain same, so no change in current. So which introduce a large resistance. Okay, and the effective resistance value we are not deriving here, and the effective resistance value looks like R out is equal to A1 into the effective resistance of that normal device without that amplifier. If this amplifier is not there, if this amplifier is not there, this will be a cascaded configuration, and its gain is R01 is multiplied with the intrinsic gain of this M2, like GM2 R02 into R01. If we use this amplifier with the gain A1, this output impedance is changes to new output impedance R out A1 is equal to the gain of amplifier into GM2 R02 R01. Okay, that's how. This amplifier we can simply implement it using a concept of a common source configuration amplifier, or any other amplifier is fine. So for example, in this case, to find the gain of the following circuit, here you can note that at node X there is an amplifier stage is connected to M2, so this will act as a cascaded configuration, cascaded with the amplifier, and which will improve the output resistance. Okay, so which will improve the output resistance. Gain of this one is nothing but GM3 R03, and the normal differential or normal output resistance here is due to M1 cascading is only GM2 R02 R01. Due to the gain of this stage, that actual output is changes to A into GM2 R02 R01 and GM3 GM2 R01 R02 and R03. This will be the effective output impedance, and due to the single input point and the current source configuration or saturation configurations, effective transconductance is GM itself, and we will get the actual gain as the product of all these elements. Okay, so here we are just improving the output resistance, here the output resistance with the help of a amplifier stage. Okay, uh, that's all. Okay, so we finished the third module also.